What I want to do here is just look at the speed of sound in waves, and we talk about this and we use it all the time, but we don't really talk about the origin of it. And I felt that maybe a brief little video here would help with that. So the speed of any mechanical wave, transverse or longitudinal, depends on two things. It's an inertial property of the medium. That's its ability, if you like, to store kinetic energy, and the elastic property of the medium. It's the storing the potential energy. So two terms we're reasonably familiar with. So with a mechanical wave, the way we write that is like this. V being the velocity of this term r, which is it's the tension in the string. So we could call that the square root of the elastic property. And we're dividing that by something we call mu, which is the inertial property. So, but what is mu? Mu then is going to be related to the density. Okay, so if we've got a thicker string, if this mechanical string, then this wave is going to travel more slowly. Bigger number here, slower. If we've got a bigger tension in the string, then it's going to travel faster. So we see that we've got these two opposing things, if you like, or two interacting things. We've got the elasticity, the tension, and we've got the inertia. It's willingness to move. It's the wave itself. So the bigger the sort of mass you're trying to move, or density, then the smaller the velocity and the higher the tension, and thus therefore the higher the amount of energy that will be stored in that, the potential energy of the elastic properties of the medium, then the faster the wave. So that's just with a mechanical wave, which we've definitely seen. So you'd need both those values to work it all out. Now with air, we come up with some other terms, and with air we write the equation with, it's very similar, but we've now got this term called B. We still have a term that relates to density. So the B is what's called the bulk modulus, and the P is the density. So again, we've got an inertial aspect to it and an elastic aspect to it. We can't see that yet because we don't know what B is. But B has this formula which goes like this: delta V over V. Now, this bottom part of the formula is change in fractional volume. So delta V over V is the fractional change in volume produced by a change in pressure. So that's what bulk modulus is. So it's for the change in pressure, how much of a fraction of change in volume do you get? So something that you apply a big pressure to and get a very small minor change in volume, what would that be like? It's like a liquid, right? Is going to have a huge bulk modulus. All right. So when we look at this formula and we look at the speed of sound in water, for example, because it's got this huge bulk modulus, that is, it's got this huge ability to only change a small amount for a huge change in pressure, we'd expect the wave to be much faster in water, which it is. But you're probably looking at that density one there and going, well, water is also much, much denser than air. So if water is 1,000 times more dense, say that's 1,000 times more for water, then we would expect the speed of sound in water to be less, but it's not, which means that the bulk modulus must be 1,000 times more, and in fact it is. And the fact that we know the speed of sound in water is about 5 times the speed of sound in air. If the density of water is 1,000, then to get that 5, I think we'd be having to look at maybe the bulk modulus being 25,000 times, right? Because we've got the square root of 25, so that would end up giving us the speed of velocity in the water being 5 times as much. So that there is just a little bit of talking about those two things. May crop up. Good to know a little bit about it.